the reinforcement learning. So first is the reward model learnings during the reinforcement learning from human feedback. So for this method, we don't ask the human to give numerical ratings for different output. For example, suppose this is a long document, and we summarize it with several short answer, and then we will ask humans to judge which one is better. And in this scenario, we will not ask a human to give numerical rating, but only give a pairwise comparison. And after that, we will use these BT models to perform comparison with the model. So the basic goal is to given this a pair of winning and losing model, we will maximum the likelihood of the winning model's score and minimize the losing answers reward model's score. So the reward model score is different from a pairwise human preference because this it only provides pairwise ranking, but this reward model, its output is real value. And we also talk about direct preference optimization. So the direct preference optimization is to address the limitation in the RLHF is that because for this second step of reward model trainings, we need to collect lots of human preference data and then train the reward model. But training the reward model is very noisy, and it will introduce bias. So after if we accumulate these errors and then perform the reinforcement learning, it will further make the training more difficult. So direct preference learning is to skip the second step of reward modeling, but directly jump to the third step. We only train the policies, but without the reward model. So the basic approach is that we will have these reward model definitions, and then we just use these reward models to plug in these loss functions. And after simplification, we will have this loss function for the pairwise ranking. So in this case, we don't need any reward functions, but we only need this pairwise ranking. So for this direct preference optimizations, we don't need to train the reward models. So now let's compare the RLHF and the DPO from a high level. So for the RLHF, it has 3 steps. The first is collect preference data, and then we perform maximum likelihood estimation to learn the reward model by maximizing the likelihood for the winning sample and the minimum the likelihood for the losing sample. And after that, we will collect the language models generation, and then we use reward models to give them score. And after give them score, we will give the feedback to the language model and update its parameters, and then it will generate the sample again. So this is an iteration process, and then we will perform reinforcement learning. But for the direct preference optimization, we don't need the second step. We don't need to train the reward model, but only directly to perform the maximum likelihood estimation for the final language model policy.
So there is no reinforcement learning in DPO, right?
Yes, right.
In the slides you have there some RL. If you go back one, like the E theta of RL, probability of RL given Y given X. I get that equation.
This one?
Yeah.
Okay. So what's the question?
So there is the RL next.
This is not an RL function, just to be consistent with the previous notation. So here there is no, this is just the fine-tuned policy. Yeah. So the possible patterns in this direction is we will heavily test on this direction. The first is how do we train the reward models in the RLHF? we will perform maximum likelihood estimation by maximizing the likelihood of the winning samples and minimum the likelihood of the losing sample. The second is we also talk about is the challenge of RLHF. Like why it make it difficult to train the RLHF. This is because human preference data is expensive to collect, and also the rating sample itself is very noisy and may introduce bias. So the third one is training the reward models also has error. So if we don't have a reliable reward models during reinforcement learning fine-tuning stage, we will not have a good fine-tuned model. The third question will be about to compare the RLHF and the DPU and to state is their procedures and compare is advantage and disadvantage. So this is a very important question for the RLHF and the DPU. Now let's summarize its comparison. So for the goal of RLHF is we train the models that we train the models to fine-tune the language model policy so that it will align with human preference. The main strategy is the reinforcement learning, but for DPU, we directly optimize the model parameters to align with human preference. And we will not use any reinforcement learning techniques. The key idea of RLHF, the core part is to train reward models on the human preference data. And the second stage is standard to the reinforcement learning. We can use any policy gradient method to update the language model policy. So one classical example is a PPU, and you can also use other policy gradient as well. So for the DPU, we directly align the human preference with the supervised learning. This will be using a same preference data, but here we don't use learn any reward function. So training pipeline on RLHF is a 3-step. The first is supervised fine-tuning to fine-tune the models on the human demonstration data. The second is reward modeling, and the third is reinforcement learning optimization. But for DPU, we only need 2 steps. The first is still supervised fine-tuning, and second step, we will skip the reward modeling and directly use the maximum likelihood estimation to learn the language policy. And the algorithm for the RHF clearly using reinforcement learning and any kinds of policy gradient we discussed in the last few lecture. But for the DPU, we can skip the reinforcement learning and use any direct likelihood based optimization. So the last part is the reinforcement learning. This is important topics. So first, we will briefly review the terminologies of reinforcement learning. So for the reinforcement learning, we have state actions. The state is a full observation of the event, but in practice, we only have a partial observation. So this O1 just like a partial observation of the state. But this does not influence the methodologies or the algorithm design. So we after that we will have a policies condition on the input state, and we will have given this input state, we will sample the corresponding action. So this policy itself it could be continuous or discrete. So if the action itself is a continuous quantity, we can use Gaussian policies to approximate distribution. But if the action itself is a discrete policy, means that we can only select a discrete set of actions from a predefined fixed set. In this case, it will be a categorical distribution. And for the this policy, it could be also probabilistic or the deterministic. So for the deterministic policies, the action, state to the action mapping is a deterministic function instead of probabilistic representation. So after that, we given this generated actions, we will move the environment to the second state, and we will repeat this process. So the reinforcement learning is different from like a standard supervised learning. This learning process is a continuous process and gradually interactive with the environment. But the learning process could be converted into like online or offline learning. So the online reinforcement learning, the learning process will continue after we observe like some reward and change to the next direction, then we can immediately perform the learning. But for the offline reinforcement learning, we can wait until the entire episode terminate. For example, it will suppose it terminate at this state. Then after that, we can like perform the offline reinforcement learning. So for the reinforcement learning, there are like several different directions. The first is model-based reinforcement learning. The model-based reinforcement learning is to model the environmental transition that given the state and actions, we will model the environmental transitions of next state given the previous state and action. But for the model-free reinforcement learning, we don't model this the environmental dynamics. So different reinforcement learning have a different trade-off and they have different use case. So we will not test so much details, but this overall landscape is very important to like remember. So the most important algorithm. Okay.
I was wondering, how does like a model-free reinforcement like learning work? Does it just not make decisions at all about which action to take?
So the don't need the transition dynamics is that during the learning process, and we will derive the equations that we don't need this part because it is cancelled during the derivation. So we only need like the sampled discrete samples from this distribution instead of like to simulate. Yeah, learning this trajectory is useful like simulate the like trajectories during the policy learning. But if we have like samples from the like trajectories, we can use direct discrete samples from the distributions to learn the policy. Yeah, we will discuss why it is. So the most important algorithm in reinforcement learning is a policy gradient. So this is the most important equations of policy gradient. It's a log derivative trick. So by using this like log derivative, it is equal to the p theta over 1 and then multiply the gradient of p theta. So this represents that the gradient of the gradient of p theta is equal to the log p theta gradient multiplies p theta. And then we will like plug in these identities in these equations into this policy gradient. So this is the most general policy gradient that using the expectations from this trajectory. So this p theta tau it represents the state action, this kind of trajectory distribution. So after that, we can see that this is very similar to the standard supervised learning gradient, but with a reward weighted gradient. And this also the like many motivations of policy gradient method. So now let's see the actual calculation process of this like policy gradient. So for example, the goal is to maximize the total reward during the entire learning trajectory. So we have emphasized that during the learning process of policy gradient, because this reward itself does not contain the like model parameters. The model parameters is only in the like policies or in this expectation distribution. So this is the most different part of optimization compared to the supervised learning. That's why we cannot directly using like the cross entropy or this kind of method to optimize this like policy function. So we model this